Okay. So let me go through it again. And now, this time, I should be able to record the screen and put it out on YouTube. And I'll have to operate underneath the Google Drive, which, here, change the folder to it. I've already got try 1, 2, and 3. Let me go back and see what try 1 was. I think try 1 was just making the beam. Then, let's see what I did for try 2. For try 2, I made the beam and deflected it. Now, I don't know how many, but maybe that was what I ended up with. So let's go back and look at what boundary condition I had for try 2. I don't know that, well, yeah, I can full screen the thing. So it should be recording this lecture. Where's that little button? Okay, so it's recording this. I can put this on YouTube later. Here, if I do that, does it go away? Can I get it back? Yeah. Go away. Okay, so the last video recording didn't work. This one, I tried this one. I think this one will work. We're going to hold it, cross our fingers. Okay, so if I go to the one that's the boundary term, which is this one right here, if I double click that one, I've got, drag it down so I can walk up to it. So I've got H times U is equal to R. H is just the identity, so that means just U is equal to R. So I've got no displacements, and either along this thing it's fixed, it's just going to be welded completely to the left wall there. The other two, there are 3 other ones. This one should give you, this one should be a Newman there. I don't know what happened there. Okay, and this one, it could be because I went back to it. It's a Newman. And then this one is a Newman, but instead of pushing it up, I think I'm going to push it down. So make it negative something, negative value. Put no spring constants in that. I may go back and put a spring constant later. So let's make it -1. And now I should, okay, so if I do that, let me make sure I've got the right, yeah, I've got the correct application. Drawing, I don't have to do any. The boundary is where I was. I think I'm okay, and I should be able to just solve it. It's somewhat deflecting off of the screen. So here, let me save it, and I think I'm going to just say, it's just T001, and I will go back and edit it. And instead of it being -4 and 8, I'll say -8 and 8. That'll make the bottom of the box a little bigger. So does that seem like it makes sense? I mean, so what I'm doing here across the top of the beam is putting a load of 1, but that's based upon the concept that the thickness that we had before was 0.001. So In other words, let's see, let me go back to that MATLAB code that was exact solution. So I had the Q was 1, my length was 50, and these numbers need to be changed, but here, I'll do it this way. The thickness here, thickness was equal to 0.001. If you really, I mean, E and I are right there, but if I had E is equal to 12 e to the 6th, I was equal to 1 divided by 12 times the base times height to the 3rd. Here, and I want to look at those and see what those are. And then say E times I. Let's see what we get there. So if you look at this thing, and those numbers aren't right, but E was 12 e to the 6th, I was 10, E times I, that's, I've got something wrong there. Oh. What did I do wrong? The thickness. I of 10, 1/12. Oh, that's L. That should be H. And I should have H is equal to 1. Try it again. Okay, so now I got that. Ignore that plot. We're going to fix those plots in a minute. So I got E, I, a tiny number. E times I is correct. And then I got that. Now the problem is if you look at the example he had, and this is, let's look at it real close. He had the example. And for some reason, oh, okay, here we go. And this is, so if you look at what he does here, he's ignore the fact that it's a curved boundary and say, well, it could be any boundary. The outward normal load, in our case, you're going to have, you know, in the beam equation, you're going to have one, you know, force per length. We need to specify traction, therefore we need to divide by the thickness, such that the surface traction should be set to that. So we want it in the load for pressure. So I need to take my Q and divide it by 0.001. So if I really want to know, here I'll do it this way. This is going to sound weird, but what should I did I spell that right? On MATLAB's PDE boundary condition. So what I'll do there is Q, let's see, if we've got that per length, that should be Q divided by T, right? Let's see what. So this says I should specify 1,000. This also says way up here. Let me make this so it no longer spits numbers at me. Okay. He says, according to this equation that we got off of the beam equation for cantilever, it should be about 780 or so. So what I'm going to do is I'm going to go back to this. Oh, but I also need the toolbox and then the boundary condition. So I'm going to go back to this and specify 1,000. I'm going to also go back to the grid, and I'm going to kind of go overboard on it a little bit, dump it, or run it. Then I'm going to basically dump the solution, go back into MATLAB, look at the maximum value of U, and I get 10. So that's not looking good. But the other thing is, if you look at it, the reason it's the maximum is, if you look, it's the minimum and maximum. The deflection occurred down. So I should do the minimum of U, and I get 770. So if I'd have done the maximum, if I'd have made it deflect upwards, it would have been okay. So in essence, to solve this problem, the one I've got, I sort of arbitrarily determined the thickness. That thickness got me my E to I. The only reason I needed the E times the I was to get an approximate solution for mechanics of materials. Other than that, it really didn't matter. But then this, what should I use to specify on PD, or the PDE boundary condition for the load, was the Q that I would input into the mechanics of materials solution divided by the thickness that I somewhat arbitrarily decided upon. Does that sort of make sense? So now I think I want to go back and do a convergent study here as well. Just a real quick set of runs. So I'll go back to this. Oops. Take the worst case scenario, run it, and then export the solution, export it. I'll tell you what, I could do something interesting. I could do minimum of U in here. It's going to give me an error. Okay, so I'll minimum of U. How about also, if you look over here in U, I'll do the length of U. So I'll run it again, not going to get much out of it. Whoops. TH. So what happened here is these last two numbers. So here is the deflection, and here is the number of degrees of freedom. So I can run it. I get one spot on the curve, so I get 1 point. So then what I'll do is go back to the PDE solver. Go back to the boundary mode. Oh, sorry, not that, the mesh mode. I hope I didn't mess up my boundary conditions. Let me double check them. Okay, they're still there, they're still good. I wanted to go back to that mode. This time I want to add some more elements. Run it again. Export the solution. Go back to the MATLAB. Run it one time. Out of it will come the new deflection. So the deflection went from minus 87 to minus 234. With 234, that's an anomaly, by the way. So if I run it, this is essentially one mesh and then the next mesh. So I'll go back again. Mesh. Go back to the mesh mode. Add another section. Run it again. Dump the solution. Go back to the MATLAB. Run it once. I'll get the new deflection. The new deflection is almost twice what the old deflection was. And that's kind of scary. So if I run this thing and I look at it in a regular linear plot, which is figure 1, I mean, here's what's so scary is this is the deflection and this is the number. So you got a real stiff beam, more elements, it softens a little bit, and it softens even more. And so what's funny is, you know, this thing is it's overly stiff compared to what it actually is. It's numerically stiff and it's softening up. That's where it's supposed to be. Okay, so let's go back to this thing again, not to that thing, to the solver. We'll go back to the mesh mode, add another refinement, run it again. Did it finish? I don't even know. Push it again. Okay. Export the solution. Go back over here, run it again, and now I'm getting this a different deflection with that many degrees of freedom. Run it again, you can see it's still softening up a little bit, but you can see this big jump in the number of elements, or the number of degrees of freedom, didn't drop. You know, if you look over here, it's almost straight line. There's no there's no guarantee that any of it's going to be a straight line, but it's probably pretty close. Go back again, go back to the mesh mode, refine it again, run it again, export the solution, go back to it, run this code once, and it printed out the new deflection. And this time it had 10,000 degrees of freedom. You can see it continuing its path, so to speak. I don't know which one you like to look at. You like to look at this one or this one, or the log. It looks like to me the log plot has a behavior which is somewhat predictable. So I can go back again. I'll keep going back through it until I get something that I'm moderately satisfied with. Add more elements, run it again. It's going to start getting slower and slower. Export the solution, go back over here, run this again, and you'll see 770. And then 40,000, over 40,000. Do at least one more. Go back to the mesh, one more, and then one more. I think past this. I don't know how much. Oh, it finished. Export the solution, head over, run this thing once to pick up the numbers. So now it's 158,000 degrees of freedom. So there you go. I think that's probably good enough. So what you start seeing is you'll start seeing it trailing off. So the solution, according to mechanics of materials, was 781. Okay, if that's 781, what was our last one that we got? 778. So now we're pretty close to it. if you look at the plots, I mean, I guess we could do one more, but I think if we did one more, you'd probably find it just goes almost straight over. So if you look at this, if you ran, here's the moral of the story is if you ran to your boss after you did the first solution, you would tell your boss the deflection was only 80, and it's 10 times that value. And so this is a scary point. Okay. Now, I know you asked the question about the boundary. Did I even answer that? I don't think I did I?
Yeah, you did.
Oh, did I?
I realized what I was doing, because if you flip back and forth between them, it sets it on the last one you've gone to. And I was going.
Oh, yeah, I have that. I've had that problem too. You got to be careful because it's, yeah, if you go here, let me save this thing. Save as TO2. O2. So if I went, let's see, if I went all the way back to the draw mode and then went to the boundary mode, oh, mine stayed there. I've had it where I go back to each of the modes and it would remove them.
Like, let's say if I just said, okay, so my Dirichlet conditions are 0 there, and then I want to make sure my Newmont conditions are 0. If I flip to the Newmont and hit OK, then it just totally ignores the Dirichlet conditions.
Oh, yeah, yeah.
I didn't realize that.
Oh, okay. Well, and then the way I start off is I'll start with the drawing. I'm going to do something kind of crazy and just say, okay, so I'll do something just absolutely nuts here. So here's something. Okay. Oh, I don't know what I did there. Oh, it doesn't like that. How about this one? Okay. And I think you can click these things and move them around. Oh, geometry error. Oh. I say that, but... Okay, so let's say I did something silly like that. Went into the boundary. Remove all subdomain. Okay, so I've got that. Am I in the boundary mode? So now I'm in boundary mode. Okay, so I've got an oddball looking thing like that. And if you look at it, they all look red. I guess they're red up there. Yes, so they're all red. And so, for some reason, I don't know why, they have decided that everything should be, the essential boundary condition or the Dirichlet or the, in this problem, displacements. But that's pretty boring because if you only have just displacements, you're not going to get anything. So what I do is Control A, select everything. And then I'll just put them all to free. So if you have a Newmont and you select, like what I did, select them all, and I have 0, 0, it's like it's a free surface. It's like it's sitting there in space, and nobody's loading it. And so then I just say, okay, they're all unloaded surfaces. And then I'll come in and hit, and I'll say this one will be fixed. I'll make the bottom of this thing fixed. And then I'll load this thing with my minus 1,000. So this will definitely be a different answer than the other one. But I should be able to now, go in here, grid it, and then run it, and you get something silly. Moderately silly. Now, in Reddy's book, he talks about this, and it's kind of a moot point, but it is true, is if you notice, if you look back at the mesh, that thing was half of a circle. So this was a circle I put in there, or an ellipse. So that's an estimate. If you click more, I think this software has it so that it tracks. You notice those little points became arcs right there. So it became more refined along there. Just for curiosity, let's see what. So it's a little smoother up there. It's not as joiny and everything. So I don't know if that answers. I mean, that's just making up something. Now you can do remember, there's one of them you have to do, or you haven't got the assignment for the 2D yet. You got the assignment for the 1D, but I'm going to make the 2D like it. Let me show if you had a software package that didn't do this. Here, let me go back to the boundary mode. So you're in, not the boundary mode, the drawing mode. So you're in here. I'm going to get some of these out of here. And let's say you had a cantilever spring over here, or a cantilever beam with a spring over here. And then you're thinking, okay, if I had a spring, and say, let's say that the E we used was still this 12 e to the 6th. And I haven't stuck to any units. You can pick any units you want. But then let's say we had a beam where this was, say, 200 force units, like pounds per inch. So this would be so much force per unit length. So in other words, if I was in English, it would be pounds, or in this case, it would be feet. So that would be my K. So K times X would be a force. Well, then X is supposed to be in feet. So if I needed this, and I don't care about what the units are, but I just know that this is going to be force per unit length. I can come in and make an object. This is if you didn't have this one feature in this. If I had this, the deflection of a bar is going to be PL over AE. Now, if you look at this thing, and you pay real close attention, looking at this, the force is P, the deflection is this. So this K from that equation would be AE over L, wouldn't it? Does that make sense? So you just take the AE and you pull the L under, and force times the stiffness is equal to, times the deflection. So now if you wanted to make a spring, and that's what I'll do, I'm kind of being unfair here. I'm going to make a spring, which I've already decided this is going to be 0.001. So I got to decide how big this is going to be. So here we'll make it 0.25. How about that? 0.25. So that means the area here will be 0.25 times 0.001. Now, if I want to know my E, it's 12 e to the 6th, and I want to know my L such that this is 200. Does it make sense what I'm doing? Yeah, I have to do mixed media here. Think about that while I do this. Since this is going to be recorded and put it on YouTube, but I wrote on the board, I got to put this on Twitter. How about that? There. Okay. So I'll say go to Twitter, and it'll record it there, so you'll know to go to Twitter. So does that make sense? Now I need to find out what L would be if I'm going to do this. So I'm just making up a problem on the fly, so to speak, but you should be able to do this. So if I bring L over into 200 across, 0.25 times 0.001 times 12 e to the 6th divided by 200. I hope this thing's not 15. It's 15, so I got to make a real thin thing that's 15. There's going to be a problem with that, but this is finite elements, and I'll tell you what the problem is going to be in a minute. So I'm going to go ahead and do that. So I'm going to go back. I am in my boundary mode, so let me go in here and just sort of draw this, and I know it's going to be the wrong size. So I'm going to try to go in and fix it. Save as, How about this? Spring 001. And not, this is spring, not winter spring. This is spring like there's a spring on the end. So now I'm going to go in here and try to fix it. Whoops, I pushed the wrong one. So I have my spring. Now see, I have two rectangles here. So if you look at this thing, I got this rectangle, which is the beam. I got this other one. Okay, I've already decided that thing is going to be 0.25. So what I'm going to do is I'm going to say, what is 50 minus 0.25? 49.75? Is that right? And then 50. And then this thing's going to, I think I better, let's see, y. Okay, so we want this. This may not work out. I may have to go back and fix it. And then I said it was supposed to be 15. So let's run it. Okay, the first thing that happened is it went off the screen. So I need to fix that. So let me go back to here and my Y limit to be 18. How about that? And now we want to see. Then I go in here. So there it is. It's a big, long, it's kind of out of context. So this little member is supposed to behave like a spring. In a PL over AE sense, if you put that load on it, you know, it is a spring. Unfortunately, it is also a beam. And we'll see that in a minute. Now, if this member was a lot thinner than that one, which it kind of is, it'll behave less like a beam and more like just a load and axial compression. But I think I better be careful about where they're touching. And let me zoom in here. I'm a little bit worrying that they're not touching, but I think they are. But I think what I really should do is just go ahead and let this thing go up to like 0.005. And I'll show you what I mean by that. So I'm kind of worried. Uh-oh, is that spring 01? See, I got it at 0.
The overlap might cause a problem.
Well, the overlap is actually okay. So here's what'll happen. Uh-oh. Oh, did I do it to the wrong one? I may have done it to the wrong one. Let's try to run it again. No. Uh-oh. Huh? Well, maybe let's see what happened here. Uh-oh. I got something that went crazy. Let me back away from it. Let me save it as spring 2. Save it as spring 2. Go back at it. This time I'll look and see what happened to it. All right, what happened to it? Okay, where's my rectangles? Wait, where is my rectangle? Am I not seeing something? That's in spring 1. That's unique, to say the least. I tell you what we'll do. Here's what we'll do. I'm going to try this. We'll try this. Just get rid of that. Save as. We'll call this spring 3. And let's run that one. Uh-oh. This is very odd. Oh, let's get rid of that one. Let's just see what happens if I do. Line 2. Oh, here. Huh? Oh gosh. I think I've blown it up. Okay, here, let's go back to the tool.
Drawing, you can double click on the rectangle and change your dimensions.
Oh. Well, yeah, maybe. Here, let me see. You mean if you're in the drawing?
Yeah.
You might be able to if you did something like this. I think you can drag it around. I thought you could. Oh. This is the weirdest thing, I'll tell you what. I don't know why he's let's go ahead and do 4. See what it's going to tell me if I do 4. I got this thing so messed up now. Let's see what I get in 4. Okay, let's take a look at this figure. And let's look back at, say, T1. Well, this is really annoying. Here, let me try to run this. Okay, that doesn't work. E2, E and E. Go back to 1. Let's compare 1 to 4. You know what? Is R1 and R2, but R1 and R2 aren't existing right there. Yeah. I don't know what happened here. Just try that. I'm in 4. It's getting, you know what? It's getting the children of that figure. If you look at 1, getting PDE figure, finding the objects of that. Let's see. Uh-oh. I'm really messing this thing up. Oh, man. Okay, hang on. What in the world? I lost my whole line there. Copy. Tag. Okay, wait a minute. Tag with the comma and the tag after it. I don't know that this is going to be any better. Toolbox axis is not found. There. Alright, I don't care about that. Okay, that's in line 2. Well, unfortunately, I may have to redraw it. But, you know what? I've got an advantage. Here's what I'll do. How about this for a trick? Alright, and I'll draw another one. I don't care what they look like. I'll go back to spring 4, dump it there, replace it. And spring 4 got replaced. Let's see. There's my 2 springs. Let me go into spring 2. Spring 1. Where'd spring 1 go? Spring 1. Grab those. Go to spring 5 or 4. Well, let's try to run that one. Alright, I was able to recover. So now at this point I think I better delete all the other miscellaneous springs. So, okay, I'm in spring 4, right? Let me run it again. I tell you what. Here's what I'll do. I'll do new. Nope, don't want to save anything. Go back to here. Run it. And it looks like I'm back where I was. Okay. I don't know. I goofed it up somehow. So let's go into boundary mode. Go into boundary mode. Zoom in here. Hopefully these things don't cross. So I should be able to go in and remove all subdomain boundaries, and that middle part disappeared. Okay, so I'll zoom back out. Whoops. Okay, so there's my funny looking structure. I'm going to Control A to select all of it. Get close to the edge. I want everything to be free. Then I'm going to come back over here and hit that one. And then I'm going to try to zoom in to the bottom and go in and hit this one so that it's fixed. Zoom back out, hit the top one, and do a -1000 again. Good grief. Now, I don't even know, did I do the application? Good, I'm still in plane stress. Okay. Alright, still in plane stress. Hit a grid. Well, I'll refine it once. Then run the solution. So you see something funny there. It's overly done, but and it's, you know, it's maybe over deflecting, so to speak. But from the way I did it, these are linear problems. First of all, I have to admit that these are all linear problems. So a 781 unit deflection on a beam is too much. So that, you know, as far as deciding to be linear or not linear, I mean, for a 50-foot long section that deflects 781, you realize that's too much. That's a nonlinear problem. So you don't want to see when you drive over the highway bridge that it's going to deflect down to the lower thing and you have to go like this over the bridge. So, but these are linear. So, but what you see is this is, you know, we put it in with the mindset that it would be a spring, but in fact, it's never really load and axial compression. It actually has a beam component to it. So you can see it's bending off there. Now, I don't know what the solution to that is as far as the numerical value, but we could find that out. So, and here's what's so ironic, you know, it still has that 5 down there. This is the deflected value because I had the deformed mesh, but still the value is probably quite a bit different than the 5 that it's showing. And for that matter, I could go back and run a bunch of them. Maybe I can't run a bunch of them. Okay. I don't know where it's at. I don't know if it's doing the gridding or if it's doing the solving at this point. I know my fan just kicked up. I may have overloaded it. Oh, there we go. So if I export the solution, I have no idea what I'm going to get. It says the maximum over here are 6 as far as vertical and minus 32. So you get, imagine that minus 32 is how far the beam dipped down. And we could find that location, which we're going to do that as well. at some point here. So I don't know if this made anything any clearer, but what you need to do is just go through the sequence several times. So what I'm going to do is next time I'm just going to give you some very rudimentary problems like the one I just did. You know, a beam that's a certain thickness, and apply the boundary conditions, and then turn it in next week. Now what I'm going to do is, I don't have everybody's first assignment, so the way I'm going to do this is I'm going to put 2 due dates on everything. The first due date is a regrade by due date. So if you turned it in before that due date, I'll grade it, turn it back, and you can turn it in before the next due date. So if you made an 85 and you get it back, you can correct it and get it regraded. But if you wait past the first due date, I won't give it back to you. So in other words, there are 4 of you that turned in the first one. So since I got those 4, I'm going to grade those, give them back to you. If you don't like your grade, you can do it again, turn it back into. So that's, since, you know, I think that's the way I'm going to do the assignments throughout the course. And you'd probably stack them like a week apart, something like that. So you turn them in, I grade them, turn them back. You do them again. If you don't want to do them again, that's fine. So, I mean, if you made a 95 and you're like, I don't want to do that again, or fix it. But if you made an 85 and you're like, I don't want, you know, I'll tell you what you need to do to fix it. So, so that gives people benefit to keeping up and turning them in early. So, let me see if this thing will work. Okay, I'm going to do a